All right, 5.4, day number 1, evaluate a definite integral by using the fundamental theorem of calculus. Typically, you'll see us use FTC. What is an integral and how is it different from an area? So we're going to go ahead and evaluate the following definite integrals. Okay, so if I were to graph part A, here's my t and f of t axes. Right, I got my t axis, my f of t axis. 60 would just be a horizontal line, right, at f of t equals 60 from, it looks like, 0 up to 3. So I've created a rectangle, and therefore the integral, which represents an accumulated area, the integral from 0 to 3 of 60 dt would be equal to 3 times 60, which would be 180. The antiderivative in this case would be 60t plus c. All right, let's look at the next one. I've got my t-axis and my f of t-axis. Ooh, we switched over on accident. F of t-axis. This time I'm going from 1 to 3. So 2t, what would 2t look like? It'd be a line with a slope of 1 with an output here of what looks like, if I plug 1 into 2t, so f of 1 would be 2 and f of 3 would be 6. So this length would be 2, this length would be 6. So the area under that curve, we could use the area of a trapezoid to be exact with that. That'd be the integral from 1 to 3 of 2t dt would equal 1/2 base 1 plus base 2 times the height. The height would be the distance between these two. So it looks like we would get 8. Okay, the antiderivative here, if I have 2t, would be t squared plus c. All right, the last one. Of course, I could sketch this. This would be a quadratic. Finding the area under the curve. I got t, I got f of t, I got t cubed plus 3, so this would be the point 3. If I go from 0 to 3, it would just be this area under here, and I have no way yet of being accurate with that. I can't calculate it exactly. I could use Riemann sums to estimate it, but it wouldn't be exact. The antiderivative here would be t cubed over 3 plus 3t plus c. Okay, so I'm going to introduce you to this thing called the fundamental theorem of calculus. And so I'll just read through this first, but I'm going to show you a way to calculate exactly that area without using Riemann sums. So recall the following relationship, right? Net area is represented by both of these things, right? Where this is our height and this is our base. And as n goes to infinity, we accumulate these areas as we get closer and closer. As delta x gets smaller, we get closer and closer to an exact area. If we were to investigate this further, we would see a connection between the net area and the antiderivative, hence why we found all these antiderivatives here. We're going to use that in the next slide. So the fundamental theorem of calculus, FTC, formally makes this connection to the antiderivative. All right, so what happens is the area under the curve from A to B gives us an antiderivative, right? We get this antiderivative f of x, and it's got a constant on the end of it, right? So it's really f of x plus some constant c. What we do is we evaluate that antiderivative at both a and b, and we take the output of f of b minus the output of f of a. So what happens in reality is we have f of b plus that constant we had on the end minus f of a plus that constant that we had hidden in this last piece, and what happens is those constants cancel out. So the area under the curve, this is actually really cool. The area under the curve can be found by evaluating f at b and at a, and that gives us a numerical answer for the area under the curve. So let's test it on this one down here. It's very powerful. Okay, so instead of sketching this, I'm just going to find the antiderivative. I can ignore the constant, that c value, and then I'm going to evaluate it from 1 to 3. So the integral from 1 to 3 of x squared dx will be x cubed over 3 evaluated. Okay, that's our antiderivative evaluated from 1 to 3. So I'll just plug a 3 in. 3 cubed is 27. So there's f of b, and f of a would be 1/3. So it looks like the area under the curve from 1 to 3 of x squared dx would be 26 thirds. So the integral from 1 to 3 of x squared dx would be 26 thirds. Okay, why don't you take a moment and see if you can do the second one, and I'll do some work off camera. Okay, so I found the derivative to be negative, or the integral to be negative cosine t from pi over 6 to pi over 2. I've evaluated that, as you can see here, plugging in pi over 2, so this is f of b minus f of a. F of b reduces to 0. F of a will reduce, it looks like, to negative root 3. And so 0 minus a negative root 3 would be positive root 3. So the area under the curve from pi over 6 to pi over 2 of 2 sine of t dt would equal square root of 3. Alright, let's try another one. It looks like we've got an integral. Ooh, now we're going from negative 1 to 3. So the integral for this would be x to the 4th over 4 plus x evaluated from negative 1 to 3. Evaluate that off camera here for a moment and see if you get the same answer I do. Alright, so when I evaluate f of b, okay, big F of b would be 3 cubed, which is 81 over 4, and 3, which is 12 over 4. I add those together, I get 93 over 4, minus f of a. When I take negative 1 to the 4th, I get 1/4, and when I plug in a negative 1, I'm going to write that as negative 4/4. So I get this 93/4 minus a negative 3/4, which is positive 96/4, which is 24. Okay, so on this next example, I'm going to find the total area analytically, not the net area. I'm going to find the net area first, but I want to draw the sketch of this graph real quick so you can see the difference in what I mean. Okay, so I've sketched this curve from 0 to 3, and it looks like part of the area will be positive from 0 to 1, and the other portion of the area will be negative. So I'm going to go ahead and find the net area real quick. The antiderivative of 1 minus x squared dx will be x minus x cubed over 3, evaluated from 0 to 3. Okay, and this is just something we've done already, so we would take f of b, which would be 3 minus 27 thirds, and subtract 0 minus 0 thirds, and what we get, I believe, is 3 minus 9, right? So this becomes 0. So I get 3 minus 9, which is negative 6. I don't want that in blue, I want it in black. Okay, so the net area is negative 6. Okay, so that's the net area. Now I want to work total area. So let's work total area here in, let's go blue. So the total area will be the sum of the blue and the green areas. Okay, same thing. But what we want to do is we want to take the absolute value of the green area. We want to make that positive and add those two together. So I'm going to do the area from 0 to 1 of 1 minus x squared dx. And I'm going to take the area from 1 to 3 of 1 minus x squared dx. And I could do the absolute value of that, or I could throw one in here and just subtract that. So that would take the opposite and change the sign of that area. Alright, so I would just be evaluating what we had up here, which is x minus x cubed over 3 from 0 to 1, and then taking what I get there and subtracting x minus x cubed over 3 from 1 to 3. So I'm going to evaluate both of these separately. I'm going to do this one in red. I'm going to do this one in blue. And then we'll subtract them and we should get a nice area. Okay, so from 0 to 1, I'll do this off camera, we'll come back, we'll analyze. Okay, so here I evaluated antiderivative at 1, which is 1 minus 1/3, and then at 0, which is 0. Subtracted those and I got 2/3. Over here I went antiderivative evaluated at 3, so I got 3 minus 27/3, and evaluated at 1, which is 1 minus 1/3. So this comes out to be negative 6 minus 2/3. So that's negative 18/3 minus 2/3, which is negative 20/3. Therefore, we get down here, we get 2/3 minus a negative 20/3, which gives us a total area of 22/3. Okay, here are the two syntaxes you can use for your calculator to find the numerical integral. This will find you the total area. So here we could have done the absolute value of those areas. This is another notation if you have an 83. If you have an 84 or an 84 plus, it kind of sets it up nicely for you. Okay, here's a homework problem finding the definite integral from 1 to 2 of 4x cubed minus 6x. I'm going to do work on the side, you can too, and then check your work. Alright, there you have it. I evaluate at 2 and at 1, take the difference, and I get 6. Let's move on to another one. Calculator now allowed. The graph of f is shown in the figure above. If the integral from 1 to 3 is 2.3, and f prime, big F prime of x equals f of x, then f of 3 minus f of 0 is... well, what this tells us, the integral from 1 to 3 of f of x dx tells me that the area under the curve from 1 to 3 is 2.3. Therefore, if I were just to take a peek at this and say, well, what would the area from 0 to 3 be? Well, I know, and I can calculate this relatively easy, the area of this rectangle is 2. So f of 3 minus f of 0 would equal the integral from 0 to 3 of f of x dx. And I've been able to find that. It's 5.3. And how would I know that? Well, that's because f of x would be evaluated from 0 to 3, which is equal to f of 3 minus f of 0. And there you have it. That would be our area. Alright, non-calculator. Integral, or the area from 1 to 2 under the curve 1 over x squared. Well, I'm going to go ahead and write this as the area, or the integral, from 1 to 2 of x to the negative second dx. So recall, I am going to add 1 when I bring that down, right? So I'm going to add 1 and divide by that same thing. And now I'm going to evaluate that from 1 to 2. Now that might not be as easy to evaluate. I might just do it this way and evaluate this from 1 to 2. Those two things are equivalent. That is equal to this. Alright, so I'm going to evaluate f of b. That would be negative 1/2 minus f of a, that would be -1. So -1/2 minus a -1, looks like it would be 1/2. Alright, calculator allowed on this one. Let f of x be an antiderivative of that. If f of 1 equals 0, then f of 9 equals what? Well, what I would know is that if I were evaluating from 1 to 9 of the natural log of x cubed over x dx, then this would give me f of x evaluated, right? Evaluated from 1 to 9. So the area under the curve, right, would actually be the same as f of 9 because I know f of 1 equals 0. So I'm going to use my calculator to find the area under the curve, and that area under the curve will give me the answer for f of 9. My calculator is giving me C 5.827. Alright, that's good for today. Fundamental Theorem of Calculus. That is 5.4, day number 1.